So, welcome to the Theoretical Neuroscience podcast, Ken Harris.
Hi, good
Hi.
to see you, Gauti. Yeah.
Yeah. So, you are professor at the University College London, right?
Yeah.
So you're and you have a lab, I guess. Yeah. So, what does your lab do?
Well, it's a co-directed lab. So the other PI is Matteo Carandini. He's in the office next door.
Mm-hmm.
And we are interested in how large numbers of neurons work together to process information. So we record from large numbers of neurons simultaneously in mice, now kind of pushing 100,000 simultaneously. And then the big part of that is analyzing the data. That's my specialty. I'm not an experimenter. I've actually never done an experiment since high school.
Good.
But processing the data is the bit I'm on.
And obviously, a lot of cool, interesting work has come out from your lab that you run together with Matteo. But because you are sort of a little bit of a if not unique, sort of rare specimen in neuroscience, or at least in experimental neuroscience, that you're originally trained as a mathematician.
Yeah,
So
that's right.
how
I
did
did a
you
math
make
degree.
a transition, or
Ooh,
what did you do, and how did you end up where you are
yeah.
now?
So it was quite a chaotic thing. So I never thought I'd go into biology. I never thought I could go into biology because the English education system, you specialize really early. And I gave up biology at 15. Gave up everything except math and physics at 15. And I got a degree in math. And I thought I wanted to do theoretical physics, supersymmetry and stuff. But I started that and I don't know, it just wasn't something I was enjoying. And in retrospect, I think it was a great decision to bail early rather than later. And then, so I had at that time because I'm an American citizen by birth, I had a National Science Foundation graduate fellowship, which I'd applied to do, to look at dynamical breaking of R symmetry in cosmological models. But the fine print said that you can do anything you want anywhere in the world, and they'll fund you for 3 years.
Wow,
So I just thought about
that's an excellent grant.
Yeah. I thought of all sorts of fields of science I could go into. I thought about the physics of water. I thought that would be an interesting thing, but it's just too hard. Water is the most complex substance you can imagine, and thought of all sorts of things, and then heard about like what then was, I guess, in its second wave of neural networks for information processing, and thought that sounded interesting. But I found that when reading about that, I really wanted to learn about the actual brain, and I'd found myself going to the library, getting a book on neural networks, and then putting it down and picking up a book on biological neuroscience. But for my PhD, I never really clocked that I could actually do that sort of work because I thought I'd need to do experiments. So I did a PhD kind of in robotics with a way of controlling a robot that was somewhat inspired by the hippocampus.
So where was this?
That was at UCL. Because I started the PhD at Rutgers, but then because I could go anywhere, I ended up at UCL. Again, I kind of bounced around about 4 labs before I ended up there, and without really much of a plan or I didn't know anyone who was a working scientist, so I had no one to kind of give me advice like how to pick a topic, and I just sort of randomly flitted about. Anyway, and I ended up doing that. And it wasn't so great, my PhD, really. It didn't make much of a splash. And I was thinking, I wasn't sure I was going to stay in science. I actually had a job because my graduate fellowship ran out, and there was no lab to fund me because my advisor had by that time left and I was working on my own.
Mm-hmm.
There was no lab to fund me. So I had to get a job. I went through the phone book, the yellow pages, and cold called the software companies saying, do you need a programmer? And the second one said, yes, when can you start? And they wanted SQL. So I got a book, Learn SQL in 24 hours.
That's some kind of database thing, or?
Yeah, it's a database programming language. I didn't know it, but I thought I could probably figure it out. And, I said I could start Monday. This was Friday. So I went out, I got Learn SQL in 24 hours and it was okay. And I was earning good money. It's only fairly recently I've started earning more than I did then, even not accounting for inflation, even in nominal pounds.
Let's see. Oh, well.
So I really wasn't sure about staying in science at all. But the one thing I thought I might do is this postdoc with Yuri Bajaki, who I'd known from when I was at Rutgers earlier. And I ended up going there and that was great, because then actually working with actual data recorded from an actual brain was so much better than building these models. And I was hooked at that point and did a postdoc with Yuri, then got a faculty job at Rutgers and then came back to England, Imperial College for a bit, and now at UCL with Matteo.
Excellent. That's good. So this should be encouraging for mathematicians out there who are.
Yeah, I mean, I've got to say, the field has been absolutely welcoming. It's not been a difficult adjustment at all. I think everyone in neuroscience knows that we need people with these quantitative backgrounds. There's a few more. There's actually quite a few of us. Mayank Mehta did theoretical physics. Clay Reid, you might not know, has a math degree. Botan Vroska. There's actually quite a few
I think
working in experimental neuroscience.
Yeah, and of course also lots of people doing all kinds of theoretical neuroscience.
Doing the modeling, but even in experimental.
Yeah. No, but
even
I think
like pure experimentalists.
Because I think if you sort of the paper we're going to talk about today, right? It's an experimental paper, but the data, they're based on experiments, but the data analysis then is quite advanced, right? So you have to be a proper mathematician. Yeah.
It uses real pure math, and I never thought I would ever use that level of math in neuroscience. And when it was happening, that project, I thought, I'm really going to enjoy this because this is never going to happen again. And it hasn't.
It hasn't.
Yeah.
Not even close.
Well, we're kind of continuing along the same lines. That using kind of functional analysis and Hilbert spaces and fractal geometry, who knows if it's going to come back, but somehow I doubt it.
Yeah. Anyway, so this is going to be this podcast is essentially, and your paper is about population coding. How does many neurons together encode information, which is sort of like the in contrast to like the single neuron coding, which is more like receptive fields and maybe the more traditional sort of way to analyze data, particularly from the days when you couldn't really measure that many neurons at the same time anyway. But then there's like different kind of hypotheses about what kind of population coding schemes that are used. And one thing that you also mentioned in the paper is this efficient coding hypothesis. So what is that? What is that about?
Okay, so this is an old idea, which goes back at least as far as Horace Barlow in the 50s, possibly older. And the idea there, it's based on information theory. The idea is that a neuron wants to communicate information using a code that gives you the maximum number of bits per spike, because the spikes cost energy, and the bits is what they want to do. So they're gonna optimize the code to transmit in terms of bits per spike. And what that means is that you don't have correlations between neurons, because if you've got two neurons encoding the same information, in a correlated manner, then one of them's wasting its spikes. So Barlow calculated and realized that what this would lead to is a very sparse code in which most neurons hardly ever fire, and a few, and those that do fire, it's always in an uncorrelated manner. And there's quite a bit of reason to think that happens in the retina. The code that is sent by the retina, from the retina through the optic nerve, has been decorrelated a lot. So, for example, the center surround inhibition that you get in retinal cells is an example of decorrelation. And adaptation is an example of temporal decorrelation. All of this kind of supports Barlow's theory, and maybe that's where Barlow got the idea from. But in the actual brain, the cortex, it's not strictly true, because we have correlations between neurons. And when I say correlations, I mean what the stimulus-dependent correlation. You can have a correlation between neurons because it's driven by the stimulus, or because the neurons are both firing independently of the stimulus. These are sometimes called signal and noise correlations. I don't really like those terms, but the stimulus-driven correlation is the similarity in the way that they encode the stimulus. And you absolutely get those in the cortex. So it shows the efficient coding isn't the full story. And one of the things we said in that paper is that pure efficient coding is absurd. And I can give an example of that. If you have a number between 0 and 1, and you encode it with 1,000 neurons, and you use an efficient code, one example of that efficient code would be that the first neuron would be a binary representation. The first neuron represents the first bit of the binary representation, the second neuron, the second bit, the third neuron, the third bit, and so on and so forth. And so by the time you've had 10 neurons encoding 10 bits, these neurons are all uncorrelated because the bits will be uncorrelated. But by the time you've had 10 neurons encoding 10 bits, you've now got the number to a precision of 1 in 1,000, 1,024, and you've used 1/100th of the neurons. So what are the other 990 of your neurons doing? They're encoding it down to a precision of around 10 to the 300, which is absurd. There's no way anything biologically would be measured to that accuracy. So an efficient code is absurd for a low dimensional signal. All the neurons are uncorrelated. It could never happen.
So one thing you say, I mean, so this efficient coding is, you say it's sparse, so you typically end up with neurons firing. And you also say that
the one I just mentioned isn't sparse.
No, I understand that. But in general, you said that what Barlow typically found.
It's not so much the sparsity as the uncorrelation. He then, he was a very smart guy. He realized basically what I just said about how you couldn't do that, and then thought, well, the only way you can have it is with an incredibly sparse code. And the kind of the idea of the grandmother cell or what have you, that at the time was a bit of a joke. Now it seems we actually have Halle Berry cells and what have you. But this came from that idea that you would have an incredibly sparse code, but you actually don't. I mean, in the cortex, now we can record there. It's not as sparse as you would need for an uncorrelated code. So that's
sort of something that I actually have a story. I have a story about Barlow because he got this. I mean, this was at this cosine meeting in Utah or something, Salt Lake City. So then there was this. He got this award, sort of lifetime award, and then he said, thanks a lot. You know what happens when you publish a great paper? And he said, nothing happens, right? Which I think was because typically that's sort of how you feel, sort of like if people take some time, even if you have a good paper, take some time before people, often take some time before people see the significance, even for Barlow. Anyway.
Is that what he was talking about in the 50s when he published this? Nobody noticed. Is that what he's saying?
So
yeah.
publish a great paper and nothing happens. So
Yeah,
that's sort of anyway. But it's also this coding means that it's high dimensional.
right.
Yeah.
Exactly. So if,
So what is meant by that?
okay, so it can mean many different things, and it's really important to distinguish them. So if you think that, okay, let's talk about three different definitions of dimension. So the first one is just the number of neurons you've got. If you've got n neurons, then their firing rates together determine a n-dimensional vector.
Mhm.
And so we can call that the ambient dimension. That's the dimension of the space that the set of firing rates lives in. Second is what you could call the manifold dimension. So if you've got a continuous stimulus, like let's say this number between 0 and 1, then that is on a line. It's on a one-dimensional manifold. But that might be embedded into the ambient space, the 1,000-dimensional space, in a very twisted way. And so but at every point locally, it looks like a curved one-dimensional or however many dimensional space. So if you have an input that has d dimensions, then the manifold dimension can't
Yeah,
really
so
be
this is
bigger than
so
d.
what is meant by input by d dimension, because that's an important thing here. So
Yeah,
d, so like if you have a number between 0 and 10, whatever, that's a one dimensional input.
that's right.
Yeah.
If you have two numbers, that's a two-dimensional. If you have a position in XYZ space, that's three-dimensional. If you have, we got error problem saving local backup of audio.
That's I think that's I don't know. I think maybe it's okay.
All right.
At least I can see some signals here. I don't know.
Okay.
Yeah.
So that's the manifold dimension. The manifold dimension might be lower than the input dimension, but it shouldn't be higher unless you've got a really pathological type of neural code.
So what is it? So that the input dimension. Repeat what you said.
Okay, so the input dimension is the complexity of the stimulus coming in. So, for example, if you're listening to a tone that has a frequency and an amplitude, that would be two dimensions. If you're looking at a color, that would be three dimensions, etc. The manifold dimension, now, the idea is that for every one of those possible inputs, every combination of tone, frequency, and intensity, for example, you've got a point in the n-dimensional space, where n's the number of neurons, that represents that input. And you can think of those points as defining a two-dimensional surface that goes through this very high-dimensional space in a twisted way, and you've got coordinates on the surface, one of which is the frequency of the tone, and the other of which is the intensity of the tone. And it makes this manifold, this twisted two-dimensional surface. And two there is the manifold dimension, because it's if you look very close around any point, it looks almost flat, and it looks like an almost flat plane of two dimensions. That's the manifold or the curved dimension. The third dimension, and this is the one the paper's about, is what you could call the planar dimension, because now the point is, if you've got this manifold that's all twisted up, it might then again lie in a flat subspace of a lower dimension. So, for example, suppose you've got a one-dimensional stimulus, just the frequency of the tone. It might be that this is curved in a two-dimensional space, but it's still in a three-dimensional space, but it still lies on a two-dimensional plane.
Okay.
Right? And that's what we're calling the planar dimension. And the reason that's important is that neurons, the neurons downstream of the cortex that are listening to this tend to take a weighted sum of their inputs. It's a linear function. And so whatever happens on a plane is the most important.
I see. So why is it that whatever happens on the plane is the most important? Why is that? I mean, it's sort of a projection, sort of.
Yeah.
It's the
Okay. Let
projection
me.
to the plane. Is that the way to think about it, or?
Yeah. Let me think about it again. What am I exactly trying to say? If it is a okay, let's put it like this.
Mm,
If it is a very high, and this is I guess one of the main messages of that paper.
mm,
If you had a neural code that had a very high planar dimension, and if the size of the dimensions, the size of all the different axes of that planar dimension um, are high, that's a pathological code, and that's kind of the mathematical result we had. And maybe we should talk a bit about that before getting onto the experimental data.
yeah. Well, yeah, we can do that. Yeah.
Or, let's put it the other way.
Mm,
Let's go the other way. So the story of the paper was that Carson and Marius, who were in the lab at the time, were collecting all of this data, and what we were looking at the time was the idea that the planar dimension would be low,
mm,
because there's all of these papers talking about how neural activity is low dimensional.
mm,
You still hear this
mm,
um, sometimes, and normally the way they do that is something like principal component analysis, and then they show a low, a small number of dimensions accounts for a lot of the variance,
mm.
um, and uh, and there was this other paper by Gao and Ganguly. I don't think it ever made it into a journal because Peiran Gao went to work for SpaceX.
Oh,
And, I'm sure he's doing great stuff there, but
yeah.
he's a loss to neuroscience.
Yeah. Oh well.
And anyway,
Mm,
they made the point that if you've got a simple stimulus, then you have to have a low planar dimension.
mm,
So, for example, if you have 10 stimuli, they have to lie in a 10-dimensional subspace or
mm,
plane. There always is going to be one.
mm,
And it's one of those things that in retrospect is kind of obvious, but just
mm,
somebody needed to say it.
mm,
And a lot of these papers in neuroscience that had found apparently low dimensional uh, representations, low planar dimension, they had to find that. It was inevitable.
okay.
So we came into this
But
thinking,
so this
well,
told, in some sense, told more about the stimulus than the.
exactly. It
Yeah.
didn't actually say anything about the neural code. It just said that the stimulus was low dimensional.
Mm,
The stimulus was simple. Therefore, the code also has to be low dimensional.
mm,
So now we actually don't know if neural activity has a low planar dimension or not.
mm.
So what Marius and Carson wanted to do was to look
But
at
just
that.
hold on before you go there, because it's. I mean, you said this. So this, in principle, this it could be high dimensional. In well, the code could be high dimensional, meaning that there are sort of many components involved, uh, and that is sort of like, as you come to it, has some issues with. Well, it has some issues with noisiness and other things, but the low dimensional thing, to begin with, the advantage a priori is maybe that it's less noisy, more robust. Was that sort of the thinking, or?
Uh, well, at the time,
Mm,
the proponents of the low dimensional theory, I don't know that it was even really about a purported advantage. It was just something they had observed.
I see. Mm,
And then, you can wonder about what the advantage of that is. I
mm,
think in retrospect, we have a theory, which we got from that paper. But at the
yeah.
time, I'm not really sure what anyone thought the advantage was, to be
Mm,
honest, of low dimensionality. It was just,
yeah. So, what were you saying, Ken?
yeah. So Carson and Marius wanted to ask whether the planar dimension was low or high. And we didn't really have a agenda on this. We just wanted to find out. And they did a lot of things that made that possible. The first thing they did, um, was to show a ton of stimuli.
Mm.
And
Well, first tell about recordings.
yeah, okay. So it's a mouse brain
Mm.
recorded with 2-photon microscopy
Mm.
in the superficial layers of the visual cortex.
Mm.
And the mouse is just sitting there watching the screen, watching the images.
So these are like layer 2, 3.
Pyramidal cells.
Yeah,
We
is
only
it
looked at the pyramidal. Since
only
then, we've
pyramid?
been looking at the interneurons. That's something we're doing more recently.
Okay, so then you have this mouse sitting there watching these images. I think it was 2,800
Something like that.
Images. I just read your paper, and they are shown for I think half a second or something like that.
Yeah, short
And,
period of time.
and then you measure the calcium signal following this presentation of this image.
Yeah,
And then you integrate it. Is then integrate the signal over some time.
yeah,
Yeah. So you
yeah,
get for each stimulus and each neuron, you get a number, which
yeah.
represents some kind of
That's right.
activity, which is sort of like maybe like some kind of spy count, something like that, or adjacent. Yeah,
So yeah, something like that.
yeah, something like that. Okay, good. So then the record is 10,000 neurons. Activity and and then what did they do, Carson?
Okay, so the key thing was there were several technical developments for the experiments. So the first is to show a ton of stimuli. The second was that in order to record a lot of neurons, they made sure they used the slow GCamp sensor, and that was important because that lets them do a slow scan rate.
So what is a GCamp sensor?
Okay, so GCamp is one of those things that when you stop to explain how all this works, you realize quite how amazing it is. So GCamp is a protein that glows fluorescent in the presence of calcium. It's genetically designed starting from the GFP protein of jellyfish, but engineered to make it calcium sensitive. And it is a protein, so the cells can synthesize it. And it has a cofactor that somehow, small molecule cofactor that somehow just finds its way into there from the cell. And so now when the cell fires an action potential, it's mainly about sodium, but a little bit of calcium comes in too. And because the calcium levels are so low in the cell normally, when it fires an action potential, suddenly you see it. And the developers of GCamp at Janelia put a huge amount of effort into trying to make it fast sensor. And but they also had this one that wasn't so fast, GCamp slow, that they released anyway. And it turns out that was the one that we really wanted, because if you want to record a lot of neurons, you've got to have the 2-photon microscope, which is another miraculous technology we could talk about.
Indeed, it is.
It scans, and the more time you give it, the more neurons it can scan.
Yeah.
And so if you want to record a lot of neurons, you have to scan slowly, which means you're only visiting the neuron about 3 times a second. So you want a sensor that's going to retain its activity for around half a second or so, so that you see it whenever your scan comes.
Yeah, cool.
And that's what the GCamp slow does. And that's what Marius and Carson figured out, is to use the GCamp slow. And then the other thing they did was to write this amazing software for processing the data. And that, brought up the number of neurons by a factor of 10. And it was just a series of small tricks. It wasn't like a radically different approach. It was just a series of small tricks that made a huge improvement over previous versions. And so those tricks enabled them to record what was then, I think, a world record in number of neurons. I don't think it is now. Well, it certainly isn't now. Yeah. And to see them in response to these thousands of images. So then, all right, we're going to ask that question we first asked about, is the planar dimension low? And the answer came in immediately, and the answer was no. Okay, fine, that's that. But
So how did you find out that? How did that come in so quickly?
okay, so another thing I need to tell you about what they realized, again, a fantastic idea, is that you need to show the stimuli twice, but you don't need to show them more than twice. So the reason you need to show them twice is there's this trial to trial variability, the stimulus independent activity. And if you only show the images once, you don't know if it's really a response to the image or a response to
whatever.
to whatever's going on in the mouse's head at that moment.
Yeah.
By showing it twice, though, twice is enough to get an unbiased estimate of the amount of variance due to that stimulus. So the reason for that is that the analysis method they came up with is you normally measure the variance of activity to measure how much is going on. But what they realized is that if instead of the variance, which is essentially the activity squared, if you took the activity on the first repeat times the activity on the second repeat, you get an unbiased estimate of the amount of variance coming from the stimulus. And the noise, it could be positive or negative, but it's going to cancel out because those are independent of each other. So it was a very simple trick in retrospect, but that's what let us isolate the part of the neural activity that's to do with the stimulus away from the part that's to do with the stimulus independent activity, which is very large in the cortex, at least as large as a stimulus dependent activity in the visual cortex. But this was the trick that let us get rid of it.
And I guess these measurements or the experiments lasted a few hours then, because you have like 2,800 images twice and about a second per image or something. Then a few hours. So that's something you can do, obviously.
Yeah. No, it's the most we're able to do is 3 hours. Okay. But that was enough for this.
Yeah.
Okay. So now back to the planar dimension. The point is that if we hadn't have had this trick, then you never know. If you look at the principal component analysis, which measures the amount of variance in the successive planar dimensions, if you don't have this trick of the cross-validation of it with the two repeats, it'll always be positive and it'll maybe go to a plateau, but you don't know if that plateau is due to real responses to the stimulus or just some stimulus independent activity.
I want to step back a little bit, because this is a critical thing. This principal components, right? And you say so say if you have 10,000 neurons, right? And then you do a principal components analysis of these data, and then you end up with like essentially 10,000 components. Principal components, and the first one is the one that picks up most of the variance. The second one is sort of like so that's and then the point is how much do sort of like the different higher components pick up, how fast does it decay with the number of the PCA.
That's right. So if you think
and you
about
call
it,
that the planar dimension, like something
kind of. I mean, if you think of what PCA is doing is, imagine something like this, right? This glass. There's one axis about it that's different to the others. That's this one. It's the long axis, right? And PCA measures basically the size of an object along this principal axis, and then it says what's next is whatever axes are orthogonal to this. And that will be this one and that one. And these have a smaller variance, a smaller size. So it doesn't matter how you rotate this in space, the sizes of the principal components, the variances, are going to stay the same. And so what it does is it measures the size of all of the dimensions. It puts them in order from the biggest to the smallest, then it measures their sizes. And if there really is a low planar dimension, then after a certain amount of certain number, those sizes are going to be 0 from then
Exactly.
on.
So if only it's like a handful of components of this 10,000 that actually carries variance,
Yeah, and the
that's a
rest will
low.
be 0. And with this unbiased estimation
Mhm.
measure, now we can really find out because we're going to get literally 0 if it is 0. And one of the key things that we did was a control experiment where we show, rather than 2,800 images, show 32 images, but lots of times each.
Mhm.
And then it really should lie on a 32 dimensional plane, because 32 points always lie on a 32 dimensional plane.
Mm.
And when we do that, we see that, yes, it does. You have 32 PCs that are large, and then it immediately drops to 0.
Yeah.
So that shows you that the method is working
Mhm.
at getting rid of this stimulus independent variability and keeping only the stimulus dependent
Mm.
part.
Cool. So then, when you did the analysis, then after these clever tricks, all kinds of sets of clever tricks, you found out that actually it's not only a few components. All components contribute, even though the contribution decays in a certain way.
Yeah, that's right. So it wasn't low dimensional. It wasn't 0 after a certain amount.
Mhm.
It was high dimensional. It never went to 0. But the weird thing is that the size of the dimension n
Mhm.
went almost like 1 over n. And you never really see this in biology. You never really see these quantitative
No.
laws. And I was sure it had to be an artifact, and
Uh,
kept trying to come up with ways. No, it can't possibly be true. It's got to be this problem. It's got to be that problem. And the two things we did that really nailed it wasn't. The first is the one I just talked about, showing 32 images 64
mm.
times. It shows it's not some sort of experimental artifact, because you don't always get it.
Ah,
And then the other one, which was that the images themselves have this sort of a spectrum. So if you take just the pixels of a set of photographs and you
mm.
put them into principal component analysis, you will get a similar dimension spectrum that goes like 1 over n. And the explanation for why came from Bill Bialek, who literally went out into the woods near Princeton and took a whole load of photos with
Okay.
a camera and then analyzed them,
Mm.
and realized quite simply that if you're taking a photo, sometimes things are near the camera, sometimes they're far away from the camera.
Mm.
And if you think about the geometry and do a bit of math,
Huh.
you can predict that whatever the objects really are, if you've got that case that sometimes they're near the camera, sometimes far
Oh,
away, you'll get this 1 over n spectrum.
do you think that would work in New York City also, on Manhattan?
Yeah, everything is close.
Yeah.
Yeah.
I don't know.
Anyway,
Anyway.
so we thought it might be that, right?
Okay.
And but then the trick there was
Mm.
to take the images and to filter them with a high pass filter, so they no longer had that property,
Mm.
but the brain activity still had the 1 over n spectrum.
So it wasn't this.
So it
It
wasn't
wasn't the
that. So
stimulus.
we're really, now we've got this weird result,
Mm.
and we couldn't figure out what it meant. And this is when the pure math came into it, because
Yay!
yeah, because and as I say, I never thought I'd use this pure math, but and when I, in my first lab at Rutgers, we had kind of a joke. I mean, it was never really put to the test. I think everyone assumed it was a joke, but the lab policy was that anyone who said the word cohomology would be immediately fired, um, because what I learned from my own advisor, Yuri Bajaki,
uh,
is that you can go down these rabbit holes of using
uh,
math just for the sake of using math. And if you have a math background, you want to use math.
yeah,
And so you enjoy using math,
I know.
but you don't actually need the math.
Mm.
And then you've got two problems. One is that it wasn't the appropriate tool, so you didn't really find very much.
Mm.
And the other is that nobody can understand what you're talking about anyway.
Mm.
So a lot of reasons not to use math. And I always tried to keep the math out of the lab.
Mm.
Yet in my spare time, just for interest, I continued reading math
Yeah, for sure.
books and had been reading this book on functional analysis by Terence Tao,
Okay.
which is absolutely great. If anyone's interested, an epsilon of room is what it's
Okay.
called. Anyway, um,
Mm.
and there was something in there that seemed possibly relevant. That is, if you have a function of y as a function of x, and you can take its Fourier transform, then the decay of the Fourier transform depends on the smoothness of the function. So if
Yeah.
the function is, let me get this right, if it's actually a well-defined function, so L zero function, I think, integrable function, then the Fourier spectrum has to decay to zero. If it's continuous, it decays as 1 over n. If it's differentiable, it decays even faster, etc. And the more times it's differentiable, the faster it decays, and it decays as a power law. The bound for this smoothness is about a power function. If the Fourier spectrum decays as if the function is to be sufficiently smooth, its Fourier spectrum has to decay faster than the appropriate power law. So that suggests there's some connection between the smoothness of the function and the Fourier spectrum. And the thing is, the principal components we've been computing are kind of like Fourier spectra.
Yeah.
If you have a circle, and your neurons all live on the circle, and suppose they have orientation tuning, they all have a preferred orientation. You can put the neurons on the circle, then your activity pattern is a function on that circle, and you do the principal components of it, you will get the Fourier spectrum. So the Fourier spectrum is like a special case of the principal component spectrum in a way. And so then that led to thinking about maybe this is something related. It's to do with the smoothness of the functions that relates to the principal component spectrum. And all this time, I was feeling very guilty about doing this because I'd got this big grant to do transcriptomics, which was something else. And, it's been a great project, and it worked eventually, but it was a huge amount of work, and it was all molecular biology, nothing to do with this at all. And they've given us a lot of money.
I think you deserve a little bit of pure mathematics on the side.
They've given us a lot of money to do this. And I was like spending all my time doing like this math that I knew, that everything I'd said about firing anyone who says the word cohomology. And so it's sort of like a guilty pleasure. But we had this experimental result of the power law. So maybe there's something to it. And I managed to prove this this theorem that if you are to have a differentiable neural code,
okay, I had to stop you there. What is a differentiable neural code?
Okay. All right. So now we need to go into some of the math. So first, let's talk about continuity. So a function is continuous if a small change in the input can only lead to a small change in the output.
Okay.
If you have a function that suddenly jumps up like this, like a step function, then however small you make the change around zero, you're going to have a huge change in y. However small the
can I think of this in terms of if you think in terms of images, that if you sort of take one of your images and then change it a tiny bit, it shouldn't change the response completely.
Exactly. So in artificial neural networks, there's a phenomenon called adversarial attack, which is incredible. If you take, and I think it still affects even the new ones. If you have a a network that's trained to classify images, let's say cats and dogs, and it gets it right 90% of the time. What you can do is you take a photo of a dog, and by looking inside the neural network, you can figure out that there's just a few pixels. You change them a tiny amount, so small that you can't see any difference in the image with your eyes. But you change these few pixels exactly the right way in a tiny amount, and now the neural network thinks it's a cat, because you trick the neural network into making a vast change in its output from a tiny change in the input.
So this is not differentiable.
Yes, right. Or rather, the derivative in terms of calculus, Newton's calculus, is the change in y divided by the change in x. Right. So in a case like that, the derivative is huge. It's vast, and one of the things we do mathematically, which is what made it so much fun, is consider the limit. The number of neurons tends to infinity, and in that limit, it's not just that the derivative is huge, the derivative is infinite, which means it's not differentiable. There is no derivative.
Yeah.
Right.
Okay.
So if you're going to have a code like this, where a small change in the input leads to a small change, can only lead to a small change in the output, then what we were able to prove is that the spectrum of the principal components needs to decay faster than a power law, where it's n to the power of 1 plus 2 over d, where d is the input dimension or the manifold dimension that we talked about at the beginning.
So let's think about that formula. If d is 1, so it's just like a very simple case, like
that would be 3.
Yeah. So then you don't. Oh, so wait a minute. So then you don't have to decay as fast. No, wait a minute.
No, then you have to decay even faster.
Even faster, exactly.
Right, because you're going like n to the minus 3.
Yeah, exactly.
In that case.
So then you have but if, like in the case of images, like and I guess it's really high dimensional because each pixel is sort of a
yeah.
So then it's essentially a 1 plus 2 over a very big number, so it's essentially 1.
That's right, and this is what we observed is 1.
Okay.
So that gave us the idea that we can actually experimentally test this pure mathematics. And so we made some stimuli that had a low dimension by taking the natural images and then basically projecting them onto these components. So it was only 4-dimensional or 8-dimensional. And we found that when we did that, actually the slope did change. So it was always on the right side of the 1 plus 2 over d boundary.
That was fantastic. That was quite a good.
It was pretty cool because you go to all of this pure math, and then you bring it back to the experiments. It was pretty.
But I mean,
fun.
now when I think about this the wrong way. But then I mean, in some sense, they are. The brain is optimized to satisfy this sort of, because what you find is it's sort of what you are saying is that it has to decay faster than 1 plus 2 over d in order to be differentiable. But it not only, but if you decay too fast, then you lose fidelity and ability to.
Right. It could decay as fast as it wants. It could decay even faster than that, and it would still not be a pathological code. No. So what we talked about at the beginning with the binary number with the uncorrelated code, that's a case of it decaying too slowly.
Yeah.
If it decays too quickly, it's not a problem from that perspective, but there's another perspective from which it is a problem. So what the brain does is one of the main things it does is associate actions with inputs, right? So you see a snake, you run, you see an apple, you eat it. But the colors are all could all be the same. It's to do with the complex combinations of patterns
Mm.
on these objects that, in a very non-linear and complicated way, leads to the desired output.
Mm.
Now, most of the learning rules we know of that might apply in the brain are linear, in the sense that the neuron downstream takes a weighted sum of its inputs,
Mm.
and it learns, through trial and error or whatever, to respond in one way
Mm.
or another. So if you're going to have a circuit that learns to fear a snake and love an apple or whatever, then you need not just to go straight from the pixels of the image, but to have some high dimensional representation so it can be read out linearly. So
Mm.
this is the idea that what the cortex does in particular is form high dimensional encodings of its input that can then be read out through a linear decoder.
Mm.
And there's a lot of evidence from that. Jim DiCarlo has some great papers on this, for example. But what we were saying is that high dimensional constraint is very good, but it also can't be too high dimensional, or
Yeah.
you have this constraint of it's no longer differentiable.
Mm.
So maybe the fact that it kind of hugs this
Mm.
constraint fairly closely
Yeah.
means it's as high dimensional as it can be without crossing the line into
Mm.
being non-differentiable.
Mm. But then you had like the I'm thinking of this the wrong way, but you had this stimuli set with different dimensions, and it worked okay for all of them, right? It's just like you should
Yeah,
maybe think that it was sort of like the brain was optimized for high dimensional stimuli and not low dimensional stimuli, so that it maybe they hugged it for high dimension for one, yeah, for when these large but not small and so on. Or am I?
yeah. I mean, so in retrospect, there's something that we realized much more recently that we didn't realize when we wrote the paper,
Mm.
which is a possible explanation for this. I mean, it's not a mechanistic biological explanation, but it's something that comes from machine learning,
Mm.
which is the Mattern kernel. I'm going to have to say what that is.
Yeah.
So there's this field in machine learning that was all the rage in the 2000s, between 2000 and 2010, when neural networks came back,
Mm.
which is kernel learning.
Mm.
And the way that works is that for every pair of possible inputs, you have a number which measures basically the similarity of those two inputs, and
Mm.
that's called the kernel function. And you can then do what I just talked about of taking the input, putting it into a high dimensional space, and then having a linear output from it. It turns out that the only thing that matters about going into the high dimensional space, the only thing that matters is the kernel function. So if you have this trick of going from an input to a high dimensional space, then with a linear readout, the only thing that matters about the projection into the high dimensional space is the kernel function, which is the similarity of the code for two inputs. All right. Now, these were and still are used a lot in all fields of data processing. And so what you do, you have to choose a kernel on your input space. So your input space might be, let's say, two-dimensional, and then you've got a function of a 2D distance that determines your kernel function. There's one that's very popular there called the Mattern kernel, and it's basically something that has a kind of a cusp at zero. And if you take its Fourier spectrum, you get a power law. And if you now have a high dimensional space of inputs, you'll get a certain, you'll get with the right Mattern kernel, you'll get a eigenvalue spectrum of PCA close to 1. But if you now take a subplane of that input, or a lower dimensional subspace of the space of inputs, and you simulate the neural population by this Mattern kernel, then you'll get that the slope of the power law increases as the dimensionality reduces, according to the formula that we found experimentally.
Cool.
So the Mattern kernel is a way of doing what it seems the brain is doing, which is taking the input and putting it into a high dimensional space, using as high dimensionality as it can before becoming discontinuous. And also doing so in such a way that if you have a lower dimensional input, the slope of the principal component spectrum increases. So it's on the right side of that bound. So when we wrote the paper, we were thinking, the brain must have some mechanism that it somehow knows it's got a lower dimensional input and it adjusts something. But actually, I don't think it has to.
No.
It can have the same code for all of these things. And I'm not saying it is a Mattern kernel. That's just an example of something with that property. And it will do this thing of increasing the slope the more, the lower the dimensionality of the input.
Yeah. Wow.
We've never published that. We need to do it.
I need to do it. Yeah, that's true. So, and also one thing that, if you think about, like you also illustrate in your paper, is that the larger the faster the decay, the larger the alpha, the smoother the manifold becomes, right? So it sort of is sort of and if it's non-differentiable, it looks like this porcupine or whatever, right? Then it's just like this manifold is just a bunch of spikes.
Yeah, which is a useless neural code.
Yeah, exactly. It's sort of so then we will be we'll be fooled by all kinds of adversarial attacks ourselves. So I don't know if you know this. I'm interested in sort of like the biophysical modeling or like mechanistic modeling of networks, and actually there are some they're using sort of this technique. There's this paper by Chen. I was like where was it? So one of it came out in 2022, Science Advances, where they actually they use this sort of like they measure it when you compare a model with experiments, right? If you want to sort of, does a model make sense? So now instead of just comparing receptive fields and so on, now we can actually compare these slopes and use that as sort of a criteria whether you get closer maybe to what the real brain.
Interesting. So I need to read that.
Yeah, no, that's an interesting because you also try to do, if you do sort of the traditional kind of analysis and fit these fit your data to sort of like these Gabor receptive fields, then you don't really capture everything.
No, you don't get it with that. No.
So it sort of is something. So this was I think it's a really cool insight, and really cool for a theoretical physicist like me to see that actually theoretical methods are useful. But this is sort of this was sort of excitatory neurons, pyramidal neurons. Have you tried to do this on other types of neurons?
So this isn't published yet, but we have done it, and the result is, let me get this right. I wish I had the graph in front of me. It's lower dimensional. It's lower dimensional in the inhibitory cells, and it's less about the stimulus, and it's more about the non-stimulus related activity, such as what the mouse is doing.
So does this mean that maybe it's sort of like the pyramidal neurons that carries most information about like the detailed parts of the image, like the
that's
interneurons
right.
are more like
the interneurons. It's not that they have no information about the image, but they have a lot less, and they have a lot more information about other stuff that's going on, and what they do encode about the image is coded in a low dimensional format.
Very interesting, because there are so many types of interneurons. So you think maybe that they are very delicate and selected and tailored, but and maybe and probably they are, but it is actually these pyramidal neurons which are seem quite similar.
Yeah.
They
So
are
so
the ones that carry the coolest information, or
the other project we were doing at the time,
mm,
which was the one that we were getting paid to do,
yeah,
was this transcriptomics
mm,
project that ended up looking at all these fine subtypes of interneurons
mm,
and and figuring out what's the same and what's different about them. And in terms of how they respond to images,
mm,
they were almost all, there wasn't very much difference between them.
mm.
But what was different between them is the way they respond to the non-visual
Ah,
inputs, what the mouse is doing.
I see.
And so Bajaki had this idea or this analogy that the interneurons are like traffic lights
Mm,
that guide the traffic through a city,
mm,
and the pyramidal cells carry the actual other cars
mm.
that carry the actual passengers
Ah,
or information.
I see.
And the interneurons are steering the information in the right direction.
Ah, well, cool. So, have you tried this? I mean, I guess now you mentioned that you're up to 100,000 neurons, I guess, now with, well, for one thing, first, you also did, this was optophysiology, right? But you
Yeah.
also did electrophysiology and got sort of the same thing, even though with fewer neurons, right?
Fewer neurons, and we weren't able to see the power law with that because you only see that when you have more neurons, but it was consistent. Yeah.
Yeah, exactly. So it doesn't sound, so that's good. But now you have up to say 100,000 neurons. Are you sort of pushing the n even further in terms of this kind of analysis, or
Yeah. So that was with there's a device called the light beads microscope from Alapasha Vaziri and amazing student we have here, Ali, built one in London
Mhm.
and has used it to collect all this data. It's still new data. We're still analyzing it. We don't
Okay.
really know
Yeah.
what's going to come out of it yet.
Are they from visual cortex also,
Yeah,
or
still visual cortex.
still
Yeah.
visual cortex? Yeah. Hmm. Yeah, so that's certainly a new exciting way to analyze this many neuron data. So about what about other cortices? I mean, I don't know if other people are pursuing this kind of analysis, or
Yeah. So it needs for this type of thing, it needs a sensory stimulus because the whole point was it identifies what's
mm,
correlated with the sensory stimulus. So you could do it in other cortices.
yeah,
The reason visual is the best for this is that you can get in so many different visual patterns very easily.
yeah,
If you were trying to do that in the somatosensory cortex, it would be
mm,
challenging.
yeah,
Auditory cortex, maybe,
mm,
but it's just so much easier in
yeah,
vision.
because it's or you can so easily get high D, sort of like a high dimension of their data.
Yeah.
Mm. So, okay, just before we started recording here, you sort of was excitedly telling about this new large language models that you have just tried out, and you can say that maybe can sort of really change the way we do science.
Yeah. So a complete change of topic now.
Yeah, absolutely.
Um, yeah, I was always rather skeptical, but the ones that came out in January are really very, very impressive. Like, so
Good.
for example, I asked Gemini 2, um, please make a web page with a JavaScript animation of surface water waves simulated by the Navier-Stokes equation.
Uh-huh.
And it said, oh, I can't do that. The
Okay.
Navier-Stokes equation is too computationally intensive
Mm.
for a JavaScript. But look, I'll use the wave equation. How about this?
Ah.
And it made a page with the surface of water with water waves that then slowly decay to nothing from one sentence. And it also said,
Uh,
I can't give you what you want,
uh,
but here's something better.
uh, uh,
And there's no reason it can't do that for neuroscience.
no.
I mean, so that's what I'm doing now
Yeah.
is getting the data from the International Brain Lab
Mm.
and getting it to analyze that. And it's a bit harder, but the reason is that documentation for that data is all over the place and it's changed.
Mm.
So the model has learned the documentation for how the data was last year,
Yeah.
and now it's changed. So that's got to,
So,
I've got to
what
write
kind of
huh?
what kind of questions have you tried asking? Sort of, give me the
Oh,
power spectrum.
download the data from one experiment and plot me an autocorrelogram.
Mm.
Plot me firing rate versus depth. These are things I did earlier today.
Mm.
Plot me firing rate versus depth.
Uh,
Do the same thing, but with the neurons labeled in color by the brain region they're in. And it could do all of those. I need to have a separate document that explains what parts of the online documentation are correct and what parts are out of date. But it's intelligent enough to do this. And I'm just going to keep pushing it as far as it goes. But I mean, it may already be at the stage where these things are as capable as your typical grad student.
Okay.
I mean, really. And if it's not there yet, it's going to be soon.
So,
and then in a year or two,
yeah,
they'll be as capable as your typical postdoc, and then they'll be as capable as your typical professor, and then they'll be beyond that. The reason is there's been a change since the original ChatGPT and the new generation. The difference is the original ChatGPT was trained by supervised learning. It just learned to predict the next word in the sentence. The new ones are trained by reinforcement learning, the same way that DeepMind built this AlphaZero that learned to play chess by playing itself. It didn't have any training at all. It just played itself. And they started going in the morning. By lunchtime, it's better than the best human in the world. They're now doing this for pure mathematics, which again, you can check by proof checking that it's valid. And this is now at International Math Olympiad silver medalist level.
Oh, really? Yeah.
And it keeps going up, and then it'll be gold, and then it'll be, Terence Tao level, and then it'll be beyond.
Oh, yeah.
And there's no reason the same can't happen for experimental science, right? It's going to be more complex for experimental science because the thing about pure math and chess is that they're checkable, right? You can absolutely certainly check when you've got a valid proof. And that's how they did it. They encode the proofs into Lean, this proof checking language, and then they can rigorously check that the proof is valid. It's going to be slower for experimental science, but it's still going to be possible because you can have an agent that you can have a big data set like the IBL data set, and the agents just analyze that, and they see when they find something.
So, I mean, you're using now, you mentioned Gemini, that's a Google thing, right?
Yeah.
And then there's also this O1 and whatever this
O1 is
OpenAI.
great. So I
Is that like similar?
I just paid the $200 a month to get O1. It's
Really?
very good. It's better.
So this
And DeepSeek, that's the one. When that came out, you remember it caused a stock market crash a few
that was a
weeks ago.
Chinese thing,
And it was when that came out, I thought, I need to check this out. Because, ChatGPT original was good. There was a whole lot of fuss do you remember about a year ago, just over a year ago, they fired the head of OpenAI.
The Altman, and that was like
and then he went and worked for Microsoft, and he said, everyone join me here, and then they rehired him. I think in retrospect, what that probably was about was when they figured out how to do reinforcement learning.
Exactly. Yeah.
They didn't say it at the time. They just said this new algorithm called Q star. And Q learning is reinforcement learning. Presumably Q star is some variant of it. So I'm guessing that's what that was in November. And then about a year later,
like the board was skeptical about pursuing this.
So because they thought it's a threat to humanity. I just watched Jeff Hinton's speech yesterday, and I can kind of see what he's saying. He's not saying that we need to stop it because he thinks it'll be impossible to stop it anyway. He's just saying what he thinks is going to happen, and he may be correct.
So what did he say that what's going to happen? Of course.
All right.
So this was this was down in Paris or something, or No, I had a friend that was on some kind of AI meeting in Paris with some.
Oh, I'm sure he goes all over the place.
Yeah.
The
Okay.
the speech I saw, it was
Yes.
in Oxford, but
Okay. Anyway. Mm.
there's also his Nobel Prize speech. He probably said the same thing
Yeah,
again.
okay. Okay. Mm. Yeah.
Anyway, um, let me get this right. So the first thing is that it's going to be smarter than us,
Mm.
and in some ways it already is. I mean, in some ways it always has been, right? I could never beat a computer at chess ever.
No.
Uh, and it can speak every language in the world. It knows a reasonable amount about every subject in the world. You know, it didn't on the first try succeed in analyzing the IBL dataset, but you know the documentation was
Yeah. The
out of
IBL
date,
is
so
the
that's
International Brain Lab.
International Brain Lab
Yeah.
dataset. So you know the documentation was out of date, so that's
Oh, yeah.
forgivable.
Mm.
So it's pretty good at
Mm.
most things.
Yeah.
And if I had asked it to translate Dostoevsky into ancient Greek, it could have done that too.
Mm.
You know, so by
Yeah.
by a lot of arguments, it's already smarter than everyone in the
What
world.
about spike sorting?
Could it do spike sorting?
Yeah.
Yeah, could ask it for. I mean, okay. So, in
Yeah.
all seriousness, I think what the future holds
Mm.
is the near future, like starting now, is a collaboration between humans
Mm.
and AI agents.
Yeah.
And the question of spike sorting is a good one, right?
Mm.
So, from what I've seen so far, if I ask even O1 to come up with a new spike sorting algorithm, it's not going to be able to do it.
Mm.
If you ask it to give a summary of all the current spike sorting algorithms, their strengths and their weaknesses, and to suggest potential new directions,
Mm.
it will be able to do that.
Mm.
And it'll say, and it might actually have a good idea. Matteo, it was a couple of weeks ago when I first tried these models, and I emailed Matteo and said, "Hey, you have to check this out."
Mm.
And he wrote back and said, "Yeah, that's amazing." Also, it saved me a conversation I was going to have with you tomorrow, because I was going to ask you what would be a good approach with this statistical problem, but it told me.
Really? So you don't need to talk to each other in the lab anymore. That's sad.
Yeah, well, I mean, it's if there's someone whose job
Yeah.
it's coming for, it's the theorist,
Yeah.
right? It's not the experimentalist. It'll
No,
be a long
that's true.
time.
No, that's
It'll be a long time till we
yeah.
have hand
Yeah.
control as good as
That's true. So the
humans.
only
But
one
it's
who keeps the job are experimentalists and plumbers and electricians. And,
plumbers, waiters,
yeah.
hairdressers,
Yeah.
anyone who can't as well work remotely.
Mm.
Anyone who could as well work remotely
Mm.
is the sort of person who needs to think what they're going to do in the next few years.
Mm.
And that's what I realized a couple of weeks ago.
Mm.
I mean, the other side of it is it's going to make us way more efficient. So the reason I'm focusing on the International Brain Lab data is it's all this data that was so painstakingly collected, and it's barely been touched in terms of the analyses that can be done with it. So this is the opportunity. And there's so many more of these. There's the Allen Institute data. You know, there's so many of these neural recording data sets just sitting there not being analyzed. That so much work has gone into collecting them.
Absolutely.
And this is the tool that's going to let us do it.
Yeah.
So this is like, as of a couple of weeks ago, you know, I think the whole direction of research has to change. That for the theorists, this is what we do.
Yeah.
We make use of all this data using AI tools.
So it's also then, of course, this it also changes how we train neuroscientists, right? It changes. I mean that's already changing how we education also. I mean, people are
there's an argument that we no longer need to teach people to program. I don't buy that. In the same way that when you do math exams at school, there's one where you're not allowed a calculator, right? Because you need to understand how these things work. And so you need to understand how programming works. And in my experience today, the debugging was a joint effort.
You and the
We did it together. There were some bits I didn't really understand. There's some bits the AI doesn't really understand. And we do all of it. And the process is to get this context prompt, which means the instructions that make up for the augment the existing documentation so it can do all of this stuff by itself. Anyway, so I still think we're going to need to educate people in how to program, how the AI systems work, etc. The other difference for education, I have this course I teach on data analysis, and we have to make the exams no AI allowed, because I used to give these programming exercises, and now the AI can do all of them. Trivial, you know.
That's true.
And so we have to make it no AI allowed, like the math exams with no calculators, because I just can't think of an exam that AI can't do.
Yeah, but that's sort of like no, but it's just like a spelling test in grade school, right? I mean, obviously,
like you have a dictionary. Yeah, exactly. Yeah,
so you cannot do that. But how? So then you have like not you have to have exams at school or at the university, and the supervised. You cannot have home exams.
Yeah, no. We last year when we did it, we literally walked around the room looking over their shoulder.
Yeah. So
this year it's even worse because we did it on Colab. Google Colab, and now Google Colab have built AI into that site.
Yeah, exactly.
So the year before, we could see, do they have ChatGPT open? Now it's going to be even harder. I don't know how we're going to do it.
Luckily, my physics exams are still in paper and
pen and paper.
Yeah,
it's going to have to be. It's back to pen and paper. I think it's going to have to be. Yeah.
Interesting. But this is a very important perspective, right? So this is sort of. So I'm very glad that you brought this up. So we should all sort of look into these AI tools and see how they can help us.
And the time is now. I mean, really, it'll take decades to filter through to all of society, but I do think it's going to be the biggest change since the Industrial Revolution. And the industry it's coming for first is science research, because the way they're trained is exactly to do reasoning about math and science and to do programming. That's what they excel at.
So also, I mean, if there's sort of like students, young people out there listening to this that sort of to learn how to use AI tools to analyze neural data,
Absolutely.
could be a good thing to bring into a lab and maybe give you a lab, because I guess it's the like the older scientists are probably having a harder time to utilize this as well as they could. So
Why?
it's probably no, I don't know. I'm just thinking in general that people are no. I mean, in general they are. I think you are sort of
okay. Here's a way to put it. Right, you know, learning a new programming language takes a long time. I finally switched from MATLAB to Python. I only use Python now, but it took a long time. Okay. Now the new programming language is English.
Yeah.
Luckily, I already speak it.
Excellent. Yeah, you know English.
Yeah. Exactly. Seriously, the new programming language is English, or Chinese, or whatever you want. But you know,
it's your mother tongue.
You could program in Norwegian. I'm sure it would work.
Yeah, I think so. Yeah. Well, this is certainly exciting times. May we live in exciting times. Isn't that what the Chinese said? And we do live in exciting times.
And we really do. The 2020s, people are going to look back on the 2020s as one of those times that is this massive period of history. Really living through history now.
That's true. Okay, Ken, thanks a lot for showing up at coming to the podcast. I don't know if you have anything you want to add before we.
No, just thanks a lot, Gauti. It was really, really fun. Really great fun.